Now that we have the velocity as a function of time, we can now find the position as a function of time. But I want you to notice something here. Notice whereas in our initial value for the velocity as a function of time, we had an initial value that the velocity at t equals 0 was only in the positive z direction. Let's see if this expression confirms that. So to confirm, we have the velocity at t equals 0 is equal to, notice the x component would be 0 times I because t is 0, and the z component is v3 plus 0 squared k hat because that t squared is 0. So yes, we do confirm that we get the original result, or the original given of the velocity at time t equals 0. Okay, so that was a quick reality check. Now that we have the velocity as a function of time, let's determine the position as a function of time. To do that, we're going to have to integrate, starting with the definition of velocity. So velocity is defined as the time rate of change of position. Well, if we integrate both sides with respect to time, and recognize that the right side of this equality ends up just being the definite integral of r of t, or the definite integral with respect to r of t, and recognize that the right side is equal to the position differential dr of t, where the integral is evaluated from r vector at some initial value of time and r vector at some later value of time. And the left side is just the definite integral from t naught to t of v of t with respect to time. So the right side of the integral works out to be the position vector as a function of time evaluated from our initial position to our function. And that is equal to, so I'm going to kind of mirror image this equation, that is equal to the definite integral with respect to time of our velocity function. Remember, our velocity function has a linear x component and a quadratic z component. And this is going to be integrated with respect to time. So the left side of this ends up with our position as a function of time minus our position at our initial value of time is equal to, now we have to integrate the right side. The x component is equal to 1/2 a1 t squared evaluated from t naught to t. The z component is equal to v3 times t, where what I'm doing here is I'm just integrating each component or each term individually. So this is v3 of t plus 1/6 a3 t cubed. And this is the z component evaluated from t naught to t. So we're almost there. We have our position vector minus our position at time t equals 0, but remember, we were given the position at time t equals 0. the position was equal to 0. So the left side is just our position function, and the right side becomes 1/2 a1 t squared minus t naught squared plus, I'm going to move this down a little bit to give ourselves a little bit more room. So this is the x component plus the z component is v3 t minus t naught plus 1/6 a3 t cubed minus t naught cubed. Now the t naughts are 0. So we have 1/2 a1 t squared for the x component, and for the z component we have v3t plus 1/6 a3 t cubed. This is our position vector as a function of time. Well, now that we have an expression for our position as a function of time, let's go ahead and go back and plug in the values for a1, v3, and a3 that we have. Remember, a1 is the x component of our acceleration function. That was given as 2.0 meters per second squared. Remember, a3 was the coefficient in front of the z component of our acceleration function, and a3 was given as 1.0 meters per second cubed. And v3 was our z component of velocity at time t equals 0, and that was given as 1.0 meters per second. With these values, we could write that the position function is equal to 1/2 2.0 meters per second squared, t squared is the x component, plus 1.0 meters per second times t plus 1/6 times 1.0 meters per second cubed, t cubed, for the z component. Simplifying, we see a 2 cancels with the 2, and we will have 1.0 meters per second squared, t squared for the x component, and 1.0 meters per second t plus 1.0 over 6 meters per second cubed, t cubed, for the z component. This is our position as a function of time. We're now able to predict where that object is going to be at any point in time. Let's do a reality check. So the reality check is that we know where the object is at time t equals 0. So let's just plug that in. I'll just say reality check for t equals 0. This should end up being 0. So when we plug in 0 for our expressions, notice the x component has a t squared in it. The x component ends up being 0. The z component, both terms have t in it, and when t is equal to 0, each of those terms is equal to 0. So yes, our function at least checks with our initial value. Now that we know the position function, let's go back to the velocity function and plug in our actual values. For the velocity component, we have a1, which is 2.0 meters per second squared t. This is the x component of velocity. The z component of velocity has v3, which is given as 1.0 meters per second, plus 1/2 a3. A3, remember, was 1.0 meters per second cubed, and this is times t squared for the z component. So we now have our final expression for the velocity as a function of time.